Okay, everybody, let's talk about the climate again, particularly about geospatial analysis. Lukas Meyer is here with us today, and he works as a project manager in the Energy and Climate Department on renewable energies and geospatial analysis at Meteotest. As we all know, during heavy storms, there is a risk of major damage to buildings. Hail, for example, can damage roofs or vulnerable subjects on roofs, such as solar panels, which is relevant for insurance companies. Meteotest has now developed a system to detect solar installations, and Lukas Meyer will now present it to you and explain it in details. Welcome.
Thank you very much. All right, hello everybody, and welcome also from my side to this talk. It's all been summarized already, basically, but it's a business presentation, so what I'll show you is really a very practical approach. So we really used all the machine learning methods that were provided by the community. So I won't show you many numbers, many model comparisons, it will be mainly pictures, which is nice for you guys. But before I get into it, maybe a brief kind of a background on why we did this work. So what you see here is a picture of a storm last summer, and you see the downburst, you see lightning, and to me as a climate scientist, it's just a very, very cool image, but actually, obviously, such storms can cause huge damages, as was the case in Switzerland in summer 2021, when you see from these media headlines that it caused tremendous damages, especially in the central part of Switzerland. And you see the last headline, it's talking about Gebäudeschäden, so damages on buildings, which is what I want to talk about today. What you see here is the damages on buildings caused by different natural hazards, and I've highlighted hail for you. And you see that it changes from year to year, depending on how bad the storm season is. But 2021, the year at the very bottom, really was by far the worst year, with damages of 780 million Swiss francs. So the question is, where do those damages occur? And a big part of the damage is obviously on roofs of buildings. Some might be on the facades, but I'll ignore that for now. And you can see here the tiles, the brick tiles, are completely destroyed. The solar panels on the right side have white dents in them. If you zoom in, this is what it looks like. And so for building insurers, this is really relevant. So they need to have information on hail and then also on roofs for successful risk assessment. And luckily today, we really kind of know where it hails. So what you see here is a hail map over Switzerland from that summer 2021. And you see these kind of, the red band showing the large risk of hail and the big hailstones. So we do kind of know where it hails and how often on average. But what about the roofs? And there's actually surprising little data on what objects are on roofs, what kind of roofs do we have. And this is where the idea came to use machine learning to get information on roofs. And we were approached by the building insurance of the Canton Zug because they said, listen, we just want a baseline, we want some kind of data on our roofs. We don't really have much. And they said, one, we need a data set of solar panels, and two, we need a data set of skylights. And I'll explain that a bit later again. So, now that that's out of the way, a brief outline of the talk. I'll show you a bit about Meteotest, the company I work for, go into the project goals, but then mainly show the data and workflow that we used to detect these objects, and if I have time in the end, show you a slide for another application using the same kind of workflow. So Meteotest is a Meteoclimate Environment Web Swiss Army knife, which basically means we do everything in that kind of space. So we have a weather forecast, a very traditional department. We have an energy and climate group, which I am part of, which focuses a lot on solar energy. We have wind, so wind energy or icing forecasts, air quality, measurements, geoinformatics, which underlies the whole thing. And then finally, obviously today, our biggest department actually is digital services, because the clients mostly they don't just want data, they want it visualized, interactive in some kind of way. So overall, it's about 40 people, and we're based in Bern. So this is an example of a project that we did, and I'm taking a big kind of reach to get to the final topic. We worked together with the Federal Office of the Environment to create the Sonnendach.ch, a public roof data set showing how good a certain roof is for photovoltaics. And you see here the Kongresshaus in Zurich has a few quite good roofs on them. And down the same vein, this is also an interactive website called blendtool.ch, which is also available for Switzerland. You can see if you place a solar panel here, where will the reflection go, which neighbors will you have to contact, who will complain, all to make planning for solar energy easier. And so we started off detecting, in object detection, by detecting roof windows for a client in the construction industry. And I won't go too much into this, but I'll try to show one issue that we had, which is the lack of reliable ground truth unless you really stand on the roof and know what you're looking at. So this is a roof tile with a roof window on it. It's fairly clear here. We could label this quite easily. But the more complex a roof gets, the more difficult it is to really be sure what you're actually labeling. And the same applies then to the solar panels and the skylights. And we started this project, and you see here the dots represent the performance of our algorithms over time. And obviously you want to be at the top right, near 100%. And first we used pixel-based pattern recognition methods, and the results were pretty mediocre, until we then switched over to these deep learning approaches, where we improved the recall and the precision quite substantially. So, what were the project goals here? We wanted to detect solar panels on roofs with an area larger than 10 square meters. This is what it looks like in situ, and then on the Swiss image, the aerial image of Switzerland. So you see there's lots of different kind of ways or types of solar panels. And the same thing goes for the skylights. They wanted to detect skylights on flat roofs with an area larger than 10 square meters. And the skylights are these kind of round glass windows that you have on industry buildings or on office buildings. And if they get old, they start to kind of rot or get weaker, and they can be damaged really, really badly by hail. And we separated them. It's a very subjective way of separating it, and we used often very crude and pragmatic approaches. We said, all right, we can see dark skylights like on the top, and we can see bright skylights on the bottom, but obviously there's stuff in between, and we said everything that's not nice and white, we just call a dark skylight. So this is kind of the data that we used. We have Swiss image, so we're really blessed in Switzerland with high quality public open data, basically. For the aerial imagery, we did some annotating on our own, and we used the Swiss buildings data set. And in the end, this resulted in the automatic detection. This is another schematic of kind of our work steps. I've blended out the analyses and apps because here the client, they just wanted a data set. We didn't have to do anything more with it. We used Python and ArcGIS environments to kind of prepare the data, to label it, to give it some attributes just for our organization. And then the machine learning approach we used was with a platform called Pictera. They're an EPFL spin-off, and it's very easy to kind of import and export data onto their platform. And we got really, really good results really quickly. And obviously this whole process is iterative, symbolized by these arrows here. So the first step was that we wanted to restrict our analyses to the roof, so we had to calculate the roof properties, mainly area and slope, and then get these tiles of the areas that we're interested in, and this is what it looks like. And then we started labeling, so we annotated 1,400 solar panels. This is an example of what that looks like, and we did the same thing for the skylights, separated again into these two classes. And then we split the data very crudely into training data and validation data to see how our algorithm performs. And another important step was to show the algorithm what is not a solar panel. For the experts among you, this is probably very clear, but I got very, very frustrated with this kind of roof because the glass roofs and the glass windows, to the algorithm, they look a lot like solar panels, and we got lots of false positives in the beginning. So we just fed it lots of images of roofs that have no solar panels on them, but many, many other complex things. Or stuff like this. You have a veranda or a terrace, and you have some kind of table or whatever that looks a bit like it. And what I can also show you on this image is that there is a shift between the aerial image and the Swiss buildings, the roof outlines. And we didn't want to cut off the top, so we buffered the buildings a bit, which then led to other issues that I'll show later on. So this is very, very simple, basic stuff. We annotated and then detected the objects on the right, obviously without showing the detector the annotations in the middle. But this kind of shows that it works very well early on. And one issue that we had is this issue of the buffer. So you see the facades on the top of the roofs, and also the shadows around the roofs were included in our buffered zone. So we got lots of false positives from that in the beginning. And so what we did, we reduced this buffer a bit, and we trained the algorithm to recognize that the facades, the top left, this raster-like pattern is not actually a solar panel, but it's some kind of facade and windows. And that worked very well in the end. So it's lots of little kind of practical issues that for us as geospatial scientists, but not really machine learning experts, we had to learn on the fly. Next, for the skylights, it's the same thing. And this example here should kind of showcase that on the right, or on the right of each image, you see there's kind of an inside area with trees, and there's some white boxes that actually could be skylights. So in the beginning, we used this building in our training data set, but we obviously decided not to use it in the end because we're not really sure. It's this ambiguity of what is actually what, and we wanted to really only feed very, very clear and data into the algorithm. So this is an example of kind of the data that we then didn't use for training because we didn't want to confuse it with that orange blob to the right. And the dark skylights, they also work very well. If there are examples like this, they have a very clear signature, so objects like these are really easy to detect early on and also to distinguish from the solar panels. One issue that we had with the dark skylights is that often other objects, I'd have no idea what this is on a balcony would also be identified as skylights. And then the big issue that we ran into is that we did these detections completely independent of each other, so we didn't use a multi-class detector or anything. So actually we got tons and tons of false positives where the dark skylight algorithm detected the bright skylights, but we told it, hey, this isn't what we're looking for. In the end, it didn't matter for us. We just wanted a data set of all the skylights. But this ruined our statistics for the dark skylights. We only got 76% precision. But in the end, we could remove those overlaps, and the final data sets looked just fine. So here are just the very baseline numbers, the precision and recall of these final algorithms. And so the precision is the percentage of detections that matched an outline, and the recall is the percentage of outlined objects which are detected. And we got really good numbers overall, except for the dark skylights, where the precision was a bit lower due to these false positives in air quotes. And this is what the final data set then looks like. In red, you see which data we actually use for training, and then in green, the final detected skylights. You have examples like this, where it worked really, really well, or also single kind of blocks of houses where the skylights were really detected good. And then the same for the bright skylights. So this is an industry area in Zug, or a bit west of Zug. You see we did label quite a bit, but overall you see really these industry roofs, they're all full of skylights that we were able to find. And the bright skylight detector is really very, very consistent. It only takes the nice and bright white skylights and doesn't really detect the dark ones. While the dark detector works really good for these black ones, but then if you have slightly grayish ones, it also takes them together. And that obviously then caused an overlap in some areas, but that's really easy stuff to fix in the end. Whenever we had an overlap, we deleted the dark skylight and ended up with a combined data set. And then one issue we still faced in the end was that we really wanted to buffer the roofs to not cut off the roof edges, but then we had a bit too much roof area, and we got a lot of false positives around the edges. So we decided to delete all the polygons of solar panels that had their center outside the original original detection, so maybe next time we don't use this buffer, since we kind of undid that step anyways. But what this did is it increased the precision a bit at the cost of deleting a few properly detected solar panels. So in total, we were able to detect 7,000 solar panels and 15,000 skylights, mostly of the type bright. We got recall and precision of around 90%. And the whole thing was about 4 weeks of work, including meetings and planning, within 6 months. So the whole thing, combining the ArcGIS and Python environment with the Picterra platform, for us was a really cost-effective, a flexible and easy-to-use approach to use this machine learning in our day-to-day business. And now that we have these detectors, we have the annotations, we can scale them to new and larger areas. And for a client, this is also important because the first kind of project might have been a bit bigger, but now whenever we get new imagery, we can do updates really, really quickly. And finally, we're going into different areas. We're trying to detect drainage ditches in bogs. So you see these black kind of scars in the landscape, the ditches that you dig to let the water drain out so you can use the area for agriculture. And this is important for biodiversity analyses, for example, because there's a big influence on the biodiversity in the bog. And it works surprisingly well. This is the very first results, but it works pretty good. And then finally, we want to use Picterra's API solutions more and more, which would allow a fully kind of automatic workflow using the Python and ArcGIS environments. Thank you very much. I hope I could give you kind of a glance into a very practical application of the machine learning solutions provided by you guys. Thank you.
Thank you very much, Lukas Meyer. Thanks for the insight. I'm wondering, what could the impact be for insurance companies?
I think what they did then with the dataset, they used the dataset in further analyses with another company that really then did lots of analyses with the house values. They looked at the frequency of hailstorms, so they know right here we have lots of skylights, and we have lots of buildings with this and this value, so they were able to then identify kind of weak spots in their portfolio, or
Okay, thank you. I'm sure there are questions in the audience. The man with the cap. Microphone is coming.
Thank you. So I'm not from the field, pardon my ignorance, but have you considered other imaging modalities, maybe, I don't know, IR images? Because I would assume that particularly solar panels have very unique characteristics, absorbance. Are these kind of data sets even available?
We didn't check this specifically for this project because it worked just fine. For example, for the bog, the drainage ditches thing, we'd much rather, or we'd also consider using the topography, so the Swiss surface data, for example. So yeah, you could use many different kind of data sets, or you could also apply some image modification techniques to really highlight the objects that you want. But no, for this project, we didn't.
Thank you.
There's one question over there.
Thank you. Just to elaborate on this last question, is there a way to distinguish between PV and solar thermal? Maybe because can be one of your false positives also.
Yeah, we looked at that in the very beginning of the project. And I must admit I wasn't on board back then, so I don't really know why they came to the conclusion that it's difficult. So maybe other people can enlighten me, but I think just with aerial imagery, it's very difficult to distinguish. I think they're both captured. I mean, the solar thermal looks a bit more homogeneous, maybe a bit blacker, is my gut feeling. I'm not sure. Maybe other imagery would be better suited.
I think that by overlapping maybe the infrared can help to distinguish between the two.
There was a question in the back there.
Thanks for the presentation. I was wondering how the different seasons of the year and the images affect the results of the model, and if you have used height information as an additional source for the detection. And maybe if you could give us an idea about what type of techniques are doing the object detection part.
Can you repeat the middle part of the question?
If height information is being used as an additional input to the model.
So height is not used. And then for the solar panel detection, we ignored the seasons completely. We took the most current Swiss image data set and we used that. For the bog, the drainage ditches, for example, there it's very relevant. So depending on if you're in the growing season, they might be covered by grass. So we are looking into older time stamps of the imagery and seeing how it performs. And we're also looking into like a normalization of the images so they look more similar. And then the model, as I said, I'm really I'm a user, so I think it's on the Pictera platform. It's ResNet is what they use, but I really don't know much more about it. It's really we create the data and we import it into the detection algorithm. Yeah.
We have time for one more question, or maybe two. There's a question over there.
Also, maybe a suggestion, less from the optical perspective. There is a data set about all PV panels geolocated from Bundesamt für Energie.
Yeah.
And then you have the installed power, and then in which houses. And then you could maybe use this one, not as an optical, but more of an administrative data set for basically confirming some of the stuff.
Yeah, I think I know which data set. Is it the one that's available as a CSV, I think, on the website, or even?
No, I mean, it's just you have like thousands of georeference data, and then it's just a shapefile, classic one. Yeah. But basically, this is the regulated part, which is registered from the Bund. So in this sense, is some kind of confirmation of what you are looking from the satellite.
Yeah, that'd be interesting. Thanks.
Thank you. No more questions? Can you imagine other benefits of using this data?
I mean, I'm more looking or thinking about extending the same analyses. So Switzerland is so kind of ahead in terms of what kind of data we have publicly. So we're thinking, could we use this to detect these type of objects or other objects in other countries, Europe, using other satellite imagery or aerial imagery?
Okay, so good luck, and this is for you. Thanks for being here. Thank you very much. Thanks.